Hello, everyone. My name is Dave Critelli, and thank you for taking the time out of your day to participate in our webinar. We hope you find the information beneficial as we discuss some application technology and some design enhancements for space. I'm sharing this presentation with Mariel Gonzalez. He's MegaPhase's chief engineer here, and together we are going to present this information.
Hello, everyone. Thank you for joining and giving us the pleasure to present this information. I assure you that you're going to be very happy when we resume all the information that we have to share today with you.
Okay, thank you. So as you may or may not know, MegaPhase is a leading RF cable and component assembly supplier for the space industry. When you're looking for a space supplier, it's important to understand that they understand and can meet all your requirements. You know, whether those requirements have to do with phase stability or matching, radiation resistance, deliver high power in a vacuum, or need some specialized ruggedization or some connector interfaces. You want to pick a supplier that can not only meet your environmental needs, but could also be a collaborative partner. MegaPhase entered the space industry about 23 years ago when we qualified Assemblies to fly on the long-duration Hayabusa space program. In this mission, a spacecraft intercepted a asteroid, it landed on it, collected samples, and returned those samples back to Earth. We've also been qualified to fly on EcoStar's Jupiter 3 satellite and the Worldview Legion Advanced Mapping satellite. In addition, we've qualified on other small and up-and-coming satellites programs. So just a quick sidebar here. We wanted to show you some of the other major programs that MegaPhase participates and supports them. Why are we showing you this information on a space webinar? Well, we think it's important when you're selecting a space systems component supplier that you fully understand their program portfolio and how those other programs and technologies might match up to what your needs are. Does the potential supplier support the technology advancements and programs that can be dovetailed into space technology that you need? These are things that we thought might be worth thinking about. You also want a supplier that can qualify against the European Space Components Coordination Specification for RF electromechanical components. This is known as the ESCC 3408 document. This specification, it's a globally recognized document and is widely referenced here in the United States. MegaPhase has qualified several components to this specification, along with our AlumaBend cable product and our Super SMA connectors. The AlumaBend is a lightweight semi-rigid cable that's approximately 40% lighter than its copper counterpart, and it's unique in that it is fully hand formable. The Super SMAs are unique in that they operate mode-free to 32 gigahertz, both the male and the female connector, but they maintain backward compatibility with the standard 18 gigahertz interfaces that meet MIL standard 348 definition. This allows for trouble-free mixing of the two interfaces. The AlumaBend is available in 3 different sizes. Each one operates at a different frequency and has a different insertion loss characteristics. These cables also have different power handling capabilities based on their unique geometries.
Part of the success story that Dave Critelli mentioned regarding AlumaBend and how we have penetrated successfully the space market and support our customer base with this product offering is the optimized Super SMA female. This concept started by recognizing the lack of high-end performance SMA females in the industry. The general connector available as a cut item, it typically is specified only to 18 gigahertz, and seldom is specified up to 26.5 gigahertz. Our space customer required precision performance up to 32 gigahertz in this particular program. Our design engineers essentially focus on an approach solution to optimize the SMA interface. And for more information, you can visit our link that we posted here in our website. And I'm going to go through the images on the right of this slide. Essentially, a classic SMA design has two matching lines from the male and the female. And we could see on the right-hand side the two arrows that point that the diameters of the male and the females do match. What engineers have done to optimize the SMA further in frequency and advance in frequency, they have designed what is called a super SMA design. And they have focused on the SMA male side. And for that, they have decreased the line size, making it a thicker wall SMA male. And for that, it's also known as a thick wall SMA or a super SMA design. But doing this particular design approach, he forgets about the other side of the story, which is the female connector. And what we create as designers making this choice is you create a larger step transition at the interface that needs to be optimized and compensated by the same gap dictated by mil standard 348. MegaPhase, what he has done, we have essentially taken the SMA female and optimized that line to match the thick wall SMA or super SMA design known in the industry on the male side, to match it with that same gap transition on the interface. That yields precision performance up to very high frequency. In this success story of this particular design, our customer feedback, and I quote, said, "Install failures on satellite subsystems are way down. What has the supplier done to change the process? Question mark." The simple answer is precision designs yield precision performance to meet customer specifications with margin, and essentially reducing the overall manufacturing and installation failure risk. And that is the design approach at MegaPhase. We design with that in mind to make sure that we have the proper margin to meet all the requirements by the customer, that even if the slight thing goes wrong, we still have plenty of margin and buffer to hit that critical value of transmission.
Now, each mission has different parameters, and having one or two product offerings may not be enough to meet every unique mission requirement. So you need to have an array of products that can be closely matched to the mission operating parameters. Whether that has to do with weight, cable size, radiation resistance, phase stability, power, signal integrity, operating frequencies, or a combination of these attributes. It's important for a supplier to be able to have a portfolio of products with different material compositions that'll match up. On the left, you can see the cutaways of the cables, and you can see the different shield layers that are offered, different ruggedizations that are offered, and different jacketing configurations that are offered. To the right in the table, you can see cable sizes, their associated weights, and associated operating frequencies. There's a lot here, so we're just going to pause for a few seconds to let you fully examine all this information. It's quite a bit. Okay, low density, oops, I'm sorry, we've gone the wrong way. Low density dielectric cables also play a significant role and offering better phase stability and lower loss than the standard solid Teflon dielectric cables. Here are a few that perform very well in these categories. Note the material and the velocity listed in black for each cable. The higher the velocity, the lower the insertion loss of the cable. Again, we'll pause for a moment just so you can compare this information.
Thank you, Dave. Another product offered by MegaPhase is the HyperFlex series. And this design has been patented in 2020 by MegaPhase. And essentially, it focuses on a fully solderless termination. Having a fully solderless option for space and ground system is the newest trend. We believe that eliminating a solder from the connector termination is the next major shift to happen in the RF cable assembly business. Having a fully solderless termination has several advantages. One of the advantages is that a solder attachment eliminates the need for expensive right angle connectors that have a lot of cumbersome transitions that affect the overall transmission of and performance of the connector. This is because without solder, you can bend the cable right behind the cable, the connector joint, effectively turning a straight connector into a right angle configuration. And the electrical performance is typically better than an actual right angle because we avoid all the transitions that are related to making a straight connection into a right angle connector in the RF transition world. Why can we bend the solder terminated assembly right behind the connector? Let's look at the anatomy of a solder joint and what goes into terminating a connector to a cable. The solder terminated assembly uses three basic parts: a connector contact, a body, and a cable. After prepping the cable, you need to solder the semiconductor of the connector to the semiconductor of the cable. And we could see that on step 2. After this subassembly is put together, you slide it into the connector body or shell and terminate the braid to the connector body. This process creates a rigid length of solder that travels up the shield of the cable. This is a natural effect caused by solder flow and heat dissipation away from the target area of that solder joint. And this is typically called in the industry as solder wicking. The solder terminated cable assembly is generally covered with a strain relief that we could see on the left-hand side on the image. And however, the intent is to transfer the stress from the solder joint that is in the second image, but this is never eliminated completely because all we do is we change the focal point from the end of the solder joint to the end of the strain relief. As stress develops in mechanical and thermal stresses, you might not realize that a fracture has occurred, and this can grow with time. This fracture risk pertains to both semiconductor and shield of the cable in a solder joint termination cable assembly. A fully solderless termination doesn't have this failure potential and allows for a worry-free bending after the connector. The HyperFlex solderless solution has an exceptional cable retention. It's as good or better than a solder termination assembly, and it can withstand up to 55 pounds of retention force. Just to put it in perspective, the SMA retention coupling ring in an SMA coupling nut is tested to 55 pounds of full retention. And that's a typical qualification for a coupling nut snap ring configuration in a typical SMA. Picture a termination of a cable withstanding this level of force. The failure point in hyperflex happens at the brace structure of the cable versus in the connector termination area itself. We achieve this higher than normal force using advanced cable shield construction. Here are some of the difference between a solder joint termination cable assembly and a purely solderless termination. And we have mentioned some of this, but we're going to go down the list to compare them. Essentially, on a solder terminated cable assembly, you cannot flex the cable right behind the connector, as we mentioned before, due to the solder wicking that forms by that color pillar flow of solder upstream into the braids. Of course, hyperflex does not have that problem and can bend right behind the connector. A solder joint can fracture on a solder joint terminated cable assembly. If you have no solder, like in hyperflex case, that risk is completely eliminated. Solder wicking length, which is something very hard to control in manufacturing environment and consistent, that's no longer the issue for high density applications where you do not use any solder like hyperflex. For space applications, X-ray inspection on solder joints are typically dictated because of solder fill and solder joint integrity and insertion of, for instance, at the semiconductor. You want to measure insertion percentage. In a purely solderless semiconductor and shield construction, like hyperflex, everything is driven by the manufacturing process and jigs and tools. So everything is predetermined before you put that connector and cable assembly together. Therefore, the X-ray inspection is not necessarily and has been avoided in the past with legacy programs. The required right angle connectors on high density applications for solder terminated cable assembly, that's no longer a requirement when you can bend the cable right behind the connector, like it is in hyperflex where there is no solder joint or wicking. And of course, solder joint termination cable assemblies have their limitation when they get dropped into a very high density box or application where you need to bend away from obstacles or different devices or panels. Then we have a hyperflex cable assembly or a solderless attachment that can bend right behind the connector and can fit in the smallest factor form possible inside the box and guarantee that at the end of that routing sequence, you're going to have a working cable, not a broken solder joint. There are 3 basic sizes on hyperflex tailored to your application, and they all vary in sizes due to the different bend radius offering and different loss characteristic based on your application. So we have an 090, a 120, and a 141, and this is the OD on top of the jacket. We can bend these cables right behind the connector at the minimum bend radius of the cable itself, which is 0.1, 0.2, and 0.3, respectively to the cable diameter OD. As we mentioned before, it's 100% solderless attachment, semiconductor and shield. There is absolutely no lead, and the reliability of the product just increases because we do not need to control solder wetting and solder fill because everything is predetermined by the solderless attachment and tooling. And essentially what that means is that this is a ROHA 6 design by configuration. We have a retention force that we specified maximum of 25 pounds, but we do measure our lots as we produce the cable assemblies, and the typical yield is between 45 and 55 pounds across the batches that we've tested. We improved the static bend radius from legacy configurations and product offerings available in the industry. For example, a low density 086 cable. The minimum bend radius is 1/2 inch. As we can see here, the equivalent product to that would be the 120 OD cable, and that's only 0.2 minimum bend radius. You can bend this cable configuration 30 times right behind the connector without degradation. It's got a configuration of a robust 3-shielded construction, ideal for RF leakage, very low RF leakage performance. Excellent return loss properties. We have optimized all this connectors transition in a solderless manner to make sure that it meets the highest standard of reflection loss and precision performance up to extremely high-end frequencies. I invite you to look at our data sheet and compare our return loss values with product offerings off the shelf and in the market in general. You'll be surprised. The ideal high-end design cable assembly, essentially this fits inside the box. You can guarantee that after the routing, it's going to perform, and based on all these characteristics that we've mentioned here. But please don't take our word for it. The intent here is to make sure that you are aware of the technologies available in the market and where the market trend is going and what the product advantages are for space applications. Try one out for yourself and be the judge.